No matter what type of aircraft you are flying, you need to make sure it is airworthy and safe to fly before you leave the ground. An organized procedure helps you check the systems and equipment in the airplane. This procedure is called the pre-flight inspection. Regardless of how many times you perform the pre-flight, always use the written checklist provided for the airplane you're flying. This step-by-step procedure ensures that you examine every item and the airplane is ready to fly. This program is designed to give general guidelines to follow during the pre-flight and engine start. Keep in mind that pre-flight procedures can vary among aircraft of the same make and model, and obviously between manufacturers. Start your inspection in the cabin by checking to see all required paperwork is in order, including the airworthiness certificate, registration, FCC radio station license, the pilot's operating handbook or the approved flight manual, and weight and balance information. Set the parking brake to ensure that the airplane will not move once the wheel chocks and wing tie-downs are removed. Next, remove the control wheel lock to free the control surfaces for the walk-around inspection. This will also expose the ignition magneto switch and avionics power switch so that you can check to ensure both are in the off position. It is important to note that the engine could fire if the ignition magneto switch is in the on position and someone moves the propeller. Turn the master switch to on. If a split rocker switch is installed, turn the battery side on to use the power to check the fuel quantity indicators and to listen for the sound of the avionics cooling fan. The indications of the fuel gauges should correspond to the actual fuel level you will check later. Once you have noted the fuel levels and verified the operation of the fan, lower the flaps and turn the master switch off. The fuel selector valve should be in the both position. By moving the selector slightly to the left and right, you should feel a detent position, which indicates the valve is in the proper position for flight. Check the baggage door to confirm that it's locked. As you move toward the tail section, inspect the general condition of the fuselage, looking for abnormalities in the skin, such as wrinkles or loose rivets. Also make sure all antennas and access panels are secure. Inspect the stabilizer surfaces for general condition, looking for dents, wrinkles, and loose rivets. Examine the control surfaces on the tail, checking for freedom of movement and security. Then, check the control cables for excess play and loose or missing safety wires. Check both sides of the control surface attachment points for loose bolts and apparent damage, and remove the tail tie-down. Continue your walk-around as you inspect the remainder of the tail section. Check the right side of the fuselage for imperfections and damage. This also provides an excellent opportunity for you to visually inspect the top surface of the wing. Next, inspect the right wing flap tracks for security and wear. Moving outboard to the wingtip, inspect the aileron hinges for security, wear, and freedom of movement. In addition, check the aileron pushrod for damage and security. Check the wingtip for possible damage and security. Then, inspect the right navigation light. Check the leading edge of the wing for dents and other damage. Inspect the attachment points of the main landing gear for dents or wrinkles. Visually check the tire for wear, cuts, abrasions, and proper inflation. Examine the hydraulic brakes and brake lines for security and leaks. With a fuel strainer, drain a few ounces of fuel from the quick drain to check for sediment, water, and any contaminants. Also, note the color of the fuel to confirm it is the proper grade for the airplane. This check should be accomplished before the first flight each day and after refueling. Some airplanes have a fuel selector quick drain and an additional fuel line quick drain located on the bottom of the fuselage. Both should be sampled and checked for sediment, contamination, water, and proper fuel grade. Remove the fuel cap and make sure the level in the tank corresponds to that indicated on the fuel gauge. The fuel cap on the right wing is vented, so visually inspect it for damage and obstructions. Then carefully check the general condition of the wing surface. During winter months and in cold climates, make sure the surface is free of frost and snow accumulation. As you move to the nose section, ensure the windshield is clean and check the general condition of the cowling. Look under the nose section for fuel or oil leaks. Check the oil level to ensure the quantity is sufficient for the flight. Keep in mind, the Pilot Operating Handbook specifies a higher minimum amount of oil for extended flights than it does for short or local flights. Pull the fuel strainer knob for several seconds to clear the strainer of any possible water and sediment. Ensure the knob is full in and closed. With the cowling secured, continue to the propeller and spinner. Carefully inspect the propeller for defects, such as nicks and cracks. Look into the inlets to make sure they are clear of obstructions. Check the alternator belt through the air inlet. Visually check the condition and ensure that it has the proper tension. Verify the landing light is intact and clean. Then examine the air filter to make sure it's clean, secured, and not damaged. Check the nose wheel tire for wear, damage, and proper inflation. Also, inspect the condition of the gear strut. Make sure the static port, located on the fuselage, is clean and unobstructed. Check the left main landing gear and drain a few ounces of fuel from the quick drain to check for sediment, water, and any contaminants. Then inspect the fuel quantity and the left wing in the same way as the right. An additional item to check on this wing is the pitot tube. Make sure the opening in the front of the pitot tube is clean and free of obstructions. An important part of the fuel system check is to make sure the fuel tank vent is open. This vent relieves pressure and allows fuel to escape from the tank during hot conditions. It also prevents a partial vacuum from forming as fuel is being used. Another important item to check is the stall warning detector on the leading edge of the wing. It should move freely and be unobstructed. You can test the warning horn by turning the master switch on, lifting the detector, and listening for the horn. Examine the left aileron and the flap for damage, wear, and freedom of movement. If you find a problem during the pre-flight, have it checked by a certified maintenance technician before you fly the airplane. Each airplane has its own unique starting procedure. The procedure itself can vary depending on whether the engine is cold, hot, or flooded, or whether external power is used. It's extremely important to use the checklist for your airplane as well as the one for the appropriate conditions. Before you start the engine, adjust your seat for comfort and visibility. Make sure the seat is locked into position and will not slip. Then, fasten your seatbelt and shoulder harness. If you're carrying passengers, be sure to brief them on how to fasten their seatbelts and shoulder harnesses, and how to latch and unlatch the cabin doors. For safety, test the brakes by pressing on the top of the rudder pedals with your toes. Then reset the parking brake. To avoid possible damage to the avionics, make sure the avionics power switch is turned off. Then visually check and slide your fingers across the circuit breakers to make sure they are in and set. As an added precaution, verify that all electrical equipment, including the autopilot, is turned off. You should now check the fuel selector, ensuring it is in the both position. In warm temperatures, 1 or 2 strokes of the primer should be sufficient. In cold weather, up to 6 strokes of the primer may be necessary. Moving back to the throttle quadrant, place the carburetor heat lever to the cold position and open the throttle 1/8 of an inch. Now, set the mixture control to rich. Visually clear the area in the vicinity of the airplane. Make sure you look behind the airplane to ensure that debris from the prop wash will not endanger people or vehicles on the ramp. Then, open the window and call out, "Clear!"
Clear!
And look and listen for a response. Turn on the master switch. Then, engage the starter by turning the ignition magneto switch to the start position. When the engine fires, release the starter switch and advance the throttle to the appropriate setting. Check the oil pressure gauge to assure that it registers adequately. If the pressure does not register within 30 seconds to a minute, shut down the engine and determine the cause. During your training, you will learn the importance of the pre-flight inspection and how it enhances flying safety. As you get ready to taxi for takeoff, you'll know that the extra time you spent covering all of the items on the checklist will help you to make sure your airplane is ready to fly. Like every other aspect of flying, you must employ special techniques when you operate on the ground to ensure you maintain control of your airplane. Let's take a look at those procedures. When you're ready to taxi, advance the throttle just enough to start the airplane rolling forward. Apply the brakes as soon as you start forward to make sure they're working properly. You'll find that more power is needed to start the airplane rolling than is needed to keep it moving. Your speed should be kept slow, especially in congested areas on the ramp. Control your taxi speed primarily with the throttle. Although applying the brakes will help you slow down, they should be used only when a throttle reduction is insufficient. This prevents excessive wear and overheating of the brakes. Steering is quite simple on most tricycle gear airplanes. Since the nose wheel is linked to the rudder pedals, applying pressure to them causes the nose wheel and rudder to deflect and turns the airplane. Because the engine is cooled by airflow, a prolonged taxi can cause it to overheat. Monitor the engine gauges closely and follow the manufacturer's recommended procedures to improve cooling. Wind blowing over the airplane and its control surfaces is another consideration when taxiing. Let's take a look at several situations and see how the flight controls are used to overcome the adverse effects of wind. There are two general guidelines you should follow. If the wind is blowing toward the front of the airplane, turn the control wheel toward the wind and apply neutral or slight forward pressure. If the wind is from behind the airplane, turn the control wheel away from the wind and push it full forward. Let's take a look at why these general guidelines are true. When you taxi into a direct headwind, the air moves equally above and below the wings. With the control wheel in the neutral position, the airplane exhibits the same stable handling characteristics as it does in flight. In a direct tailwind, moving the control wheel full forward places the elevator in the down position. In this situation, the wind strikes the upper surface and exerts pressure on the top of the elevator. This prevents the tail from being lifted and the airplane from nosing over. A wind from the side, such as this quartering headwind, tends to lift the upwind wing and roll the airplane. When you turn the control wheel into the wind, the upwind aileron moves up and the downwind aileron moves down. The wind flowing over the control surfaces tends to push the left wing down, the right wing up, and counteracts the tipping tendency. If the wind is behind the airplane, as with this left quartering tailwind, you'll need to position the controls differently. Again, the wind tends to lift the upwind wing. It also tends to lift the tail. In this situation, move the control wheel opposite the wind direction and apply forward pressure. This raises the right aileron, lowers the left aileron, and places the elevator in the down position. As the wind blows across the airplane, the aerodynamic forces created by the displaced ailerons and elevator will counteract the rolling and tipping tendencies. The wind flowing over the airplane changes as you turn, and you'll need to reposition the control surfaces. Always be aware of the wind direction. Even in very light winds, position the controls appropriately. After taxiing to the run-up area, align the nose of your aircraft into the wind. Try to keep the propeller blast away from the other aircraft. Using a printed checklist from the aircraft manufacturer, make sure every item is checked and nothing is omitted. Whether you set the parking brake or hold the brakes with your feet, you should divide your attention between cockpit duties and outside the aircraft to make sure it doesn't start moving forward during the run-up. Make sure the cabin doors are closed and locked. Also, close and lock both windows. When you turn the control wheel to the right aileron will move up, and the left aileron will move down. Conversely, turning the controls to the left will move the left aileron up and the right aileron down. To help you remember which aileron is up, place both hands on the control wheel and move it to the right. If you extend your thumbs, they will point to the aileron in the up position. Pulling back on the control wheel will cause the elevator to move up, and pushing forward on the control wheel will move the elevator down. To check the rudder for proper operation, depress the right rudder pedal and it will move the rudder to the right. Left rudder pedal pressure will cause the rudder to move to the left. Next, check and set your flight instruments. Set the altimeter to the current altimeter setting, or if the current setting is not available, adjust it to the field elevation. Check and adjust your attitude indicator to ensure the miniature aircraft is in a wings level position on the horizon bar. Set the heading indicator to the magnetic compass indication. Place the fuel selector valve to the fullest tank or to the both position, as recommended in the pilot's operating handbook. Now, set the elevator trim to the takeoff position. Smoothly advance the throttle to the appropriate RPM and adjust the mixture control as required for the field elevation, or as recommended in the pilot's operating handbook. If your pilot's operating handbook has an amplified procedures section, refer to the section on leaning the mixture for high-altitude operation and high field elevations. To check the magnetos, move the ignition switch first to the right position and note the RPM drop. Move the switch back to the both position and then move the ignition switch to the left position and note the RPM drop. Return the switch to the both position. Switching from both magnetos to the left or right magneto individually should cause the engine RPM to drop. In most cases, a drop of around 125 RPM is acceptable for individual magneto operation. However, the difference between the left and right magneto drop should not exceed 25 to 50 RPM, depending on manufacturer's recommendations. If you don't get a drop in RPM, it may be the result of a faulty magneto ground wire, and the aircraft should not be flown. Apply carburetor heat and check for a drop in RPM. Then return the carburetor heat control to the off position. In some geographical areas with high humidity or visible moisture, you can experience carburetor ice while taxiing. This may be noted by a larger initial drop in RPM followed by a slight increase in RPM. The initial drop may be accompanied by engine roughness, which should subside with the RPM increase. Check the suction gauge. It should be indicating between 4.5 and 5.4 inches of mercury. Now, check the ammeter. The ammeter shows the charging rate applied to the battery. If the alternator is not working or the electrical load exceeds the output of the alternator, the ammeter indicates the battery discharge rate. Reduce the power back to idle RPM and begin an avionics check. Check the transponder. For a VFR flight, you should use the code number of 1200 in your transponder. However, some tower-controlled airports have special local procedures and may assign a discrete code. Once you have confirmed the transponder code, check the communication and nav aid frequencies. Quickly review the performance airspeeds and departure procedures and finish the checklist items. Of course, airspeeds and procedures will vary with aircraft. Correct procedures are those recommended in the pilot's operating handbook for your aircraft. Release the parking brake. Always check for other traffic before you leave the run-up area, including the final approach path, taxiways you may cross to get to the runway, and the runway itself. Remember, opposite direction traffic may be in effect. You should also check for traffic when departing a tower-controlled field. Proper engine shutdown requires that you use the appropriate checklist, just as you did for the engine start. Make sure the radios, electrical equipment, and avionics power switches are turned off. Then, place the mixture control in idle cutoff. When the engine has stopped, turn the ignition magneto and master switches off. Next, install the control lock to prevent wind gusts from damaging the flight controls. Then, be sure to place the fuel selector valve in the left or right position to prevent cross-feeding. It's important to remember that your flight is not complete until the airplane is secure. In some cases, you may have to move the airplane into the tie-down space by using its tow bar. As you steer the airplane, remember that it is sometimes difficult to judge how close the wingtips and tail are to other aircraft or obstacles. You may want to have someone at the wingtips to help guide the airplane. Once you're in position, place wheel chocks in front and behind the main wheels to prevent the airplane from moving. You should also make certain that the wing and tail tie-downs are properly secured. A key element to a safe, successful flight is maintaining positive control of your airplane. This is just as important on the ground as it is in the air. By taking the time to learn proper ground operations, you will be adding to your skills as a competent pilot.
One of the first in-flight skills you will learn is how to control your airplane by using outside visual information. This program introduces the reference points you will use and explains how to combine them with your flight instruments to maintain straight and level flight. As the name implies, straight and level means flying a constant heading at a specific altitude. Airplane control in this situation is divided into two basic elements: pitch control and bank control. Your primary reference for determining pitch information is the view forward through the windshield. This is the normal pitch attitude for level flight. The distance between the nose and the horizon is a measurement of your pitch attitude. As your pitch attitude is increased, the distance between the nose and the horizon becomes smaller. As your pitch attitude is decreased, the horizon moves higher and further away from the nose. Using a point on the windshield that is on or near the horizon is also a good reference for your pitch attitude. Your pitch attitude can also be seen when you look at the wingtips. By comparing the angle of the wing to the horizon, your flight attitude is readily apparent. This is how a nose-high pitch attitude looks. And this is a nose-low pitch attitude. You can also verify the pitch attitude by referencing the flight instruments. The attitude indicator is an instrument that graphically shows your relationship to the horizon. This bar represents the horizon, and this symbol represents your airplane as viewed from behind. When you are in a level flight attitude, the airplane should rest on the horizon bar. When you increase the pitch attitude, the airplane symbol in the attitude indicator moves above the horizon. In a nose-low attitude, the airplane symbol moves downward, duplicating the attitude you see outside. Two other flight instruments you use to cross-check your visual references are the altimeter and the vertical speed indicator, or VSI. The altimeter shows your flying altitude and verifies that you are flying level. Any deviation in your altitude is indicated by movement in the needles. The VSI tells you if you are level, climbing, or descending. It also shows how fast you are climbing or descending. When the needle is at 0, the airplane is in level flight. Now that you have seen how to maintain level flight, let's look at how to keep the airplane flying in a straight line. To maintain straight flight, you must control the bank attitude of your airplane. One way to tell if you are flying straight is to note the position of the horizon in the windshield. You can detect a deviation from straight flight by noting when the horizon tilts in the windshield. In addition, both wingtips should appear to be an equal distance from the horizon. When the wingtips are equal, you are flying straight. As with pitch attitude, you can cross-check your visual cues with the attitude indicator. A turn is shown when the horizon bar tilts in reference to the miniature airplane. When the airplane and the horizon bar are aligned, the airplane is in straight flight. You can also determine if you are flying straight by looking at the heading indicator. A change in heading tells you are banked. Another instrument that detects a bank is the turn coordinator. Unlike the attitude indicator, the turn coordinator does not tell you the angle of bank, but rather tells you how quickly you are turning and the direction of the turn. Your ability to maintain straight and level flight by outside visual references will soon become second nature. This skill will help lay the foundation for almost all of the maneuvers you will learn.
The same reference points you use to help maintain straight and level flight will be used to help you establish climbs, descents, and turns. Let's begin with a look at how to perform climbs. As with straight and level flight, the best visual reference for pitch information is the position of the nose relative to the horizon. To start a climb, smoothly apply back elevator pressure to raise the nose. As the pitch attitude increases, you will experience a decrease in airspeed. For this reason, add power as you increase the pitch to establish the climb. When you have set the proper pitch and power, the airspeed will stabilize at the correct climb speed. Any deviation in pitch will cause a change in airspeed. Decreasing the pitch attitude increases the airspeed, while raising the pitch attitude causes a decrease in airspeed. The flight instruments confirm the climb by a nose-high position on the attitude indicator, an increasing altimeter, and a positive rate of climb on the vertical speed indicator. Another visual indicator of a climb is the positive angle created by the wingtip and horizon. In a climb, you need right rudder pressure to overcome the aerodynamic forces that tend to make the airplane turn to the left. If you do not maintain enough rudder pressure, the ball in the inclinometer will move to the right. You can correct this by applying right rudder to bring the aircraft back into coordinated flight. To return to straight and level flight, you need to anticipate the level off before you reach the desired altitude. One method is to lead your desired altitude by 10% of your rate of climb. Here, your rate of climb is 500 feet per minute. 10% of 500 is 50. Based on that rate of climb, you should begin your level off 50 feet before you reach your desired altitude. The references you used for a climb are the same references you will use to establish a descent. Descents are practiced to help you learn how to lose altitude without gaining excessive airspeed. Two types of descents are practiced: those at approach airspeed and those at cruise. To transition from cruise to a descent at approach speed, you must first lose airspeed. To do this, reduce the power and maintain altitude by increasing back elevator pressure. This helps reduce the airspeed to the proper approach speed. When you reach the correct airspeed, lower the nose slightly to maintain that speed. The pitch attitude in this type of descent will be almost level or slightly nose down. Any change in the pitch attitude will cause a corresponding change in your airspeed. To descend at cruise airspeed, lower the nose at the same time you reduce power. As with the previous descent, maintain airspeed by adjusting the pitch attitude. Use the VSI again to calculate when to begin your level off from a descent. Use the same 10% rule described earlier to identify the level off point. You begin a turn by rotating the control wheel in the direction you want to turn. Once you have initiated the bank, it will continue to become steeper until you neutralize the control wheel. Holding neutral control wheel pressure keeps the aircraft in a constant bank angle. When you want to roll out of the turn, use opposite control wheel pressure. Due to the aerodynamic force of adverse yaw, you must use rudder pressure in the direction of the turn to keep the aircraft in coordinated flight. The position of the horizon in the windshield is the best outside reference for the turn. By keeping this reference stationary in the windshield, you will be able to hold the aircraft in a constant bank attitude. A turn to the left looks like this from your viewpoint. Notice how the horizon is positioned in the windshield. A right turn will appear different from a turn to the left. One of the most notable differences is that with the same bank angle, the nose will appear to be higher in a left turn than in a right turn. Another factor that influences the position of the horizon in the windshield is the amount of bank. As it increases, you lose more vertical lift. To compensate, you must increase the pitch attitude to maintain level flight. In addition to your visual references, the airplane's flight instruments can also verify that you are in a turn. The attitude indicator, heading indicator, and turn coordinator will also verify that you are in a turn. When you are rolling out of a left turn to a specific heading, you should lead your rollout by about half your bank angle. In other words, if you are in a 30-degree bank and you want to roll out on the heading of 090, you should begin your rollout at 105 degrees or 15 degrees before the desired heading. Now that you've seen how climbs, descents, and turns are performed, let's combine them into a single maneuver. The climbing turn is simply a combination of a turn and a climb. The easiest way to combine these two maneuvers is to start with the climb. First, establish the proper pitch attitude and power setting for climb. Then roll into your desired bank. As you become more proficient, this combination will become more natural, and you will be able to do both steps simultaneously. When returning to level flight, you should level off when you reach your altitude and return to wings level flight at your desired heading. To perform a descending turn, first establish your pitch attitude and power, and then roll into your desired angle of bank. As you reach your target altitude, level off, then roll back to a wings level attitude on your desired heading. When you combine the fundamental maneuvers of climbs, descents, and turns, you have the ingredients to perform most flight maneuvers.
As your flight training progresses, your instructor will give you the flight controls more often and let you take command of the airplane. At first, a takeoff may seem complicated, but soon you'll perform each takeoff with ease. Before any takeoff, however, you need to complete the pre-takeoff checklist. When you have completed the checklist, contact the tower for takeoff clearance. Then check the traffic pattern, including the arrival and departure paths for other aircraft. As you taxi onto the runway, align the airplane with the center line and roll forward enough to center the nose wheel. Choose a point that is aligned with the runway. Use it as a reference for maintaining runway heading after you're airborne. This is a good time to turn on your transponder. Also, make a quick check of the windsock to verify the wind direction and speed. To prevent inadvertent use of the brakes during takeoff, slide your feet down so that the balls of your feet are on the lower part of the rudder pedals. Begin the takeoff roll by applying full power. As the airplane accelerates, glance at the engine instruments and the tachometer to confirm that takeoff power is available. If the winds are calm or are directly down the runway, keep the ailerons neutral during the ground roll. As the airplane accelerates, maintain directional control with smooth, positive rudder pedal pressure. Rudder effectiveness will increase as the airspeed increases. As the airspeed approaches liftoff speed, smoothly apply back pressure to rotate the airplane to the takeoff attitude. In most training airplanes, this attitude is similar to the normal climb attitude. Maintain this attitude until the airplane lifts off the runway. With the proper attitude, your airplane will become airborne near the climb speed. You should then adjust this pitch attitude to maintain climb airspeed. Maintain the runway heading until reaching a safe turning altitude. At this point, if you plan to stay in the traffic pattern, initiate a turn to the crosswind leg. If not, depart the area according to local procedures. The The previous takeoff discussion assumed that the wind was light or directly down the runway. But what do you do if you have a crosswind? A crosswind tends to push and roll the airplane to the downwind side of the runway. The nose of the airplane will also have a tendency to turn into the wind. This is known as weather vaning. Some manufacturers provide crosswind component charts which list the maximum demonstrated crosswind component velocity. Before beginning the takeoff roll, check the windsock to determine the wind direction, and then position the ailerons into the wind. Full aileron deflection may be required at low speeds when control effectiveness is minimal. As the speed increases and the ailerons become more effective, you may gradually reduce the amount of aileron deflection. Hold the airplane on the runway until attaining a slightly higher than normal liftoff speed. At this point, establish the normal climb attitude by applying elevator back pressure. When the airplane is airborne, make a slight coordinated turn into the wind to establish a drift correction, or crab angle. Once the correction is established, level the wings and maintain the drift correction angle to climb out along the extended runway center line. As you practice takeoffs in various wind conditions, you will become increasingly comfortable with them.
One of the most important places you'll apply the skills of straight and level flight, climbs, descents, and turns is in the traffic pattern. Each runway has its own traffic pattern. The traffic pattern is a rectangular course located adjacent to the runway. It is used to keep landing and departing aircraft in an orderly flow and definite path about the airport. Traffic patterns have several segments or legs. The downwind leg runs parallel to the runway and is flown in the opposite direction of landing. Most of this leg is flown in straight and level flight. As you approach the end of the downwind leg, you begin a descent, then make a descending turn to the base leg. The base leg is flown in a straight descent. When you near the extended center line of the runway, you make another descending turn. The final leg is a descent along the extended center line until landing. When you take off, the straight-ahead climb is called the takeoff or departure leg. Like the final, it is flown along the extended center line of the runway. If you elect to depart the pattern, you can either fly straight out or turn 45 degrees from the departure leg. If you are returning for landing, you can make a climbing turn to the crosswind leg. Notice that all the turns made in this pattern are to the left. This is a standard left-hand traffic pattern recommended by the Aeronautical Information Manual and is the most common type in use. When turns are made to the right, it is called a right-hand traffic pattern. It's used for a number of reasons, such as keeping traffic away from noise-sensitive or dangerous areas. They are also used at airports that have parallel runways. In this situation, the right runway will have a right traffic pattern. This allows for simultaneous approaches and prevents the two runway traffic patterns from overlapping each other. Now that you have an understanding of the basic left-hand traffic pattern, let's look at how to use it. Most entries into the traffic pattern are made by intercepting the downwind leg at a 45-degree angle to the midpoint of the runway. Before you reach the entry point, you should be at the traffic pattern altitude, which is usually 1,000 feet above the airport elevation. As you approach a non-towered airport, monitor the common frequency and look for any traffic that may already be in the area. Look for airplanes that are turning onto downwind from the crosswind leg. In addition, be alert for airplanes that are flying a wider or closer pattern than yours. Also watch for slower airplanes ahead of you that can create a spacing problem. Before entering the downwind leg, announce your intentions on the common frequency.
Longmont traffic, Cessna 66091, entering downwind for runway 29er, touch and go, Longmont.
Upon intercepting the downwind leg, turn and fly parallel to the runway. Your heading should be approximately 180 degrees from the runway heading. This leg is flown between 1/2 to 1 mile from the runway. The point on the downwind leg, when you are abeam your intended landing spot, is where you generally begin your descent. Upon reaching the position approximately 45 degrees from your intended landing spot, check to make sure there is no other traffic already established on the base leg. Then begin your turn.
Longmont traffic, Cessna 66091, base, runway 29er, touch and go, Longmont.
The base leg is flown with a ground track which is 90 degrees to the runway. Once you're on the base leg, you will decide if your approach needs to be adjusted for wind or traffic. Before you turn onto final, make sure there is no other aircraft established on the final approach path.
Longmont traffic, Cessna 66091, final, runway 29er, touch and go, Longmont.
When you roll out on final, you should be no closer than 1/4 mile from the runway. This leg is flown directly along an extended center line of the runway. When you depart a runway, you should continue straight out along the extended center line until you are past the departure end of the runway and within 300 feet of the traffic pattern altitude. At this point, you have the option of departing the pattern straight out or making a 45-degree turn away from the departure leg. You can also make a climbing turn to the crosswind leg and return for another landing. In either case, you should announce your intentions. At a tower-controlled airport, the controller may specify the type of departure to be flown, or you can request a specific type of departure. When you approach a tower-controlled airport, you may also be asked to fly a modified traffic pattern to keep the traffic flow smooth. For example, a controller may ask you to enter and report base leg. If so, you should not fly the normal downwind, just the base and final legs of the approach. In this program, you have learned how basic flight maneuvers are used to fly the traffic pattern. These skills are the foundation for learning good approach techniques.
Landings are a challenging but rewarding part of your flight training. A well-executed landing demonstrates that you have the ability to perform basic maneuvers, plan approaches, and use proper landing procedures. A typical landing approach in a training aircraft begins when you enter the downwind leg at a 45-degree angle, about mid-field to the runway. Usually, you're at cruise speed. By entering the pattern at mid-field, you have sufficient time to establish a track parallel to the runway and stabilize your attitude and airspeed. Once you're established on downwind and have completed your pre-landing checklist, you can use your heading indicator to help you maintain the proper distance from the runway. You can do this by visualizing the landing runway superimposed over the heading indicator. For example, if 29 is the landing runway, you can fly a parallel but opposite course by flying the reciprocal heading of 110 degrees. When at a point opposite the intended landing spot, you normally reduce power and maintain your altitude until the airspeed slows to the initial approach speed. If you intend to use flaps during the approach, lower them to the first increment when the airspeed is within the white arc. The use of flaps allows you to make a steeper approach without increasing airspeed. It also allows you to touch down at a slower speed with a corresponding shorter ground roll. Throughout the approach, use trim to relieve control wheel pressure. When the airplane slows to the approach airspeed, begin a descent. However, maintain the downwind heading until your intended point of landing is approximately 45 degrees behind the aircraft. Then initiate a medium bank turn. A glance at your heading indicator will help you determine the proper rollout point. You already know that the base leg is approximately 90 degrees from the runway. So when the visualized runway is 90 degrees off the nose of your aircraft, you are on the correct heading. During the base leg, lower the second increment of flaps if they are being used, and adjust the power as necessary to maintain the desired approach path and airspeed. Complete the turn to final so that the airplane is aligned with the runway. At this point, adjust your final approach to intercept the glide path. Lower the final increment of flaps and trim the airplane. If precise control is maintained throughout the landing, the time from power reduction to the touchdown phase will be approximately the same on each approach. During the touchdown phase, you will need to flare or rotate the airplane to the touchdown attitude. At approximately 10 to 20 feet above the runway, initiate the flare by applying gradual back pressure on the control wheel. This decreases the rate of descent and airspeed. As you begin the flare, reduce the power to idle if you haven't already done so. The airplane should reach a 0 rate of descent when the main wheels are just off the runway at an airspeed just above a stall. The attitude at touchdown should be very close to the takeoff attitude. The main gear should touch down first, with the nose gear clear of the runway. After touchdown, maintain back pressure to prevent abrupt nose wheel contact with the runway. After the nose wheel has settled to the runway, gradually relax the back pressure to provide positive nose wheel steering. Throughout your training, you should try to be as consistent as possible to reduce the number of adjustments needed in the traffic pattern. However, you may have to alter the pattern for local procedures or for proper spacing behind other aircraft. If adjustments are required, you can make them in several ways. You may vary power or change the starting point of the descent. You may also extend the downwind or delay flap extension. The earlier you recognize a need for adjustment, the smaller the correction will have to be. To fly a consistent pattern, you must compensate for the effects of wind. In order to do this, you must be able to fly a straight line over the ground, regardless of the wind direction. If there is no wind, tracking a straight line is nothing more than pointing the nose of the airplane in the direction you want to fly. However, if the wind is blowing at an angle to your flight path, it will blow you off course unless you take corrective action. You will need to position the nose of the airplane into the wind just enough to stop the drift. The angle formed between your heading and the ground track is called the crab angle, or wind correction angle. How much you crab into the wind will depend on the direction and speed of the wind, as well as your direction of flight and airspeed. For example, if the wind is directly down the runway, you must crab the airplane into the wind on the base leg. If you don't apply any correction, the airplane will drift further from the runway, increasing the length of the final approach leg. Strong winds not only affect the base leg, but also have a marked effect on the final approach. When you turn into the wind on final, your ground speed is reduced. However, the rate of descent remains the same. If you make no corrections, touchdown will be short of the intended point. Therefore, use additional power and increase the pitch attitude slightly to maintain the proper glide path and approach. After the correct glide path is established, try to maintain a constant approach angle. In this way, the apparent shape of the runway will remain fixed. A shorter, wider shape indicates you're low on the approach, while a longer, narrower shape indicates you're too high. If the approach is high, the normal reaction is to lower the nose and dive the airplane at the intended point of landing. While this may increase the rate of descent slightly, the most pronounced effect is that it will build up excessive airspeed, which significantly reduces the time it takes to descend. Therefore, the airplane will still be high as it approaches the threshold. In addition, the excess speed requires time to dissipate, so the airplane may float well beyond the touchdown point. The proper corrective action is to reduce power, extend additional flaps if available, and maintain the proper approach attitude and airspeed. This should increase the rate of descent without reducing the time to the threshold. Another way to lose altitude is to use a forward slip. This is accomplished by lowering the upwind wing and applying sufficient opposite rudder pressure to displace the nose of the aircraft toward the high side of the bank. This increases drag by presenting a larger surface area to the relative wind, with a corresponding increase in the descent rate. If you use a forward slip to lose altitude, establish a normal descent before making the transition to the touchdown phase. Not every one of your landings is going to be perfect. Therefore, you need to know what to do if your approach and landing are something other than normal. For example, if the airspeed is low during the flare, you should delay the power reduction. This will help prevent a rapid loss of altitude with a high sink rate and possibly a hard landing. Conversely, if airspeed is higher than normal, maintain just enough back pressure to keep the airplane in level flight until the excessive airspeed is dissipated. Then continue the flare until the airplane touches down. Flaring too early or too late can also present a problem. If you begin the flare too soon, the airplane may stall prior to touchdown. The resulting high sink rate and hard ground contact may result in structural damage to the landing gear and its supporting structures. If you flare too early, add power and stabilize the attitude in a position from which you can make a normal landing. However, if insufficient runway remains, initiate a go-around. If your flare is started too late, you may touch down at a high rate of descent and the airplane may bounce. If the airplane bounces just a few feet in the air and you have plenty of runway left, you might consider placing the airplane back in the landing attitude, adding a little power and letting the airplane settle back onto the runway. Under many circumstances, however, it is best to initiate a go-around by applying full power and adjusting the pitch to the takeoff attitude. Then when you have enough airspeed, make a normal climb out. If the flaps are extended, slowly retract them as the airplane gains altitude and airspeed. As you gain experience, you will develop the ability to analyze and recover from an awkward situation and make a normal landing. But if you're ever in doubt about the outcome, a properly executed go-around is your best bet. An approach and landing in a crosswind is essentially the same as an approach made into a headwind, except that now you need to compensate for the wind drift. Each leg of the traffic pattern may require a crab angle to maintain a straight ground track. Before landing, however, you will use rudder to align the fuselage with the runway centerline. At the same time, lower the upwind wing just enough to maintain the desired ground track. The result is a side slip into the wind, producing a wing-low, straight ground track that keeps the airplane over the runway. In this example, the crosswind is from the right. Early in the final approach, turn the airplane's nose into the wind and maintain a straight ground path. Before landing, however, lower the right wing into the wind and apply opposite rudder to align the nose with the center line. Execute the flare exactly as you would if the wind was straight down the runway, except now the upwind main gear will touch down first. As the airplane decelerates, continually increase the aileron deflection to prevent the upwind wing from rising. When you have mastered the procedures presented here, you will be able to land the airplane consistently and safely in crosswind situations.
General aviation aircraft are among the safest and most reliable forms of transportation in the world. But like any machine, failures can happen. Your training is designed to introduce you to a variety of simulated systems and equipment malfunctions and give you the tools to cope with that rare occasion when a malfunction occurs. During your practical test, the examiner gives you up to 3 simulated systems and equipment malfunctions to test how you analyze the situation and to see if you take the appropriate action to resolve the problem. The list of possible systems and equipment malfunctions varies from a partial or complete engine failure to smoke or fire in the engine compartment. Typically, procedures for emergency situations can be found in your POH or AFM. However, it is impossible to cover every failure or malfunction. If your POH or AFM does not have procedures for a specific emergency, such as an asymmetrical flap extension, you must rely on previous experience, good judgment, and a knowledge of the manufacturer's published emergency procedures to form an appropriate plan of action. Remember, as in any emergency situation, your first priority is to fly the aircraft. You must remain calm, clearly assess the emergency, then respond quickly and accurately to fix the problem. While many emergency checklists are committed to memory because your response must be instantaneous, other situations are less critical. In this case, you have time to refer to the POH or AFM to determine the appropriate course of action. An example of an emergency that is typically not covered in a POH or AFM is the partial loss of engine power. The partial loss of power could be the result of any number of factors, including a mechanical breakage or stoppage of the throttle control, or even undetected ice. Depending on the degree of power loss and to what extent the performance of the aircraft has been compromised, you may have several different options regarding your course of action. If your aircraft is capable of maintaining altitude or climbing, you can continue your flight to the nearest suitable airport while monitoring engine instruments and looking out for an emergency landing site should the need arise. You should maintain at least best glide speed while you attempt to restore full power to the engine. This may include applying carburetor heat, readjusting the mixture, checking the fuel selector switch, checking the magneto switch, and making sure the primer is in and locked. If you are unable to restore power, continue flying until you reach a suitable landing site. If your performance is severely diminished, you may have no other choice than to execute an off-airport landing. You should follow the emergency landing checklist outlined in your aircraft POH. It's a good idea to discuss emergency procedures for a variety of possible situations with your flight instructor. Your instructor can help you develop guidelines for systems and equipment malfunctions that are not covered in your AFM or POH. Reviewing emergency procedures on a regular basis and repeated practice with your flight instructor will also help prepare you for a real system malfunction or failure. In the unlikely event of a systems or equipment malfunction, your preparation can be the difference between confusion and a favorable outcome.
Engine failures in today's general aviation airplanes are extremely unlikely. Chances are you will never have to perform an emergency approach and landing, but you should always be prepared for an unexpected emergency. Let's take a look at how you can do this. The Emergency Procedures section in the Pilot's Operating Handbook is your official source of information on how to handle an emergency. You need to review the emergency procedures in the POH often enough to ensure that they come to mind quickly. For an extra margin of safety, you should always practice emergency approach and landing procedures with an instructor. Remember that emergency approach and landing procedures may vary slightly between different airplanes, so you should consult the POH for the airplane you fly. Now, let's take a look at some general emergency approach and landing procedures. The first thing to do, if you sense a loss of engine power, is establish the best glide speed. This speed can be found in the POH. If you fly at the best glide speed, you will minimize altitude loss, giving you more time to deal with the emergency. Flying at any speed faster or slower than best glide will result in a greater rate of descent. To help maintain the best glide speed, use the trim to relieve control pressures. The next step is to locate a suitable landing spot. If an airport is not located close by, look for an open pasture, sod farm, or hard-packed dirt field. Some roads make good landing spots. However, be aware of hazards such as cars and power lines. Avoid fields that are plowed or have ditches and other obstructions. You should also take the wind direction and speed into consideration when choosing a landing spot. A shorter field with a strong headwind may be a better choice than a longer field that has a crosswind or tailwind. After you have selected a good landing spot, go ahead and make a turn toward it. Make sure the spot you've selected is close enough to glide to comfortably. It's better to circle over your selected site if you need to lose altitude. This will also aid you in picking out any obstacles such as potholes, power lines, or ditches. If you have time while gliding down to your landing spot, you should attempt to figure out what's wrong with the engine. In case ice has formed in the carburetor, pull the carburetor heat to the on position. Verify that the fuel selector is in the both position. Adjust the mixture. Make sure the ignition switch is in the both position and check the primer to verify it is in and locked. If the engine doesn't start, continue with your emergency approach. If you have time after an attempted restart, try to notify someone of your emergency. Set your transponder to 7700. If you are in contact with ATC, call on the currently assigned frequency and advise them of your situation. If not in contact with ATC, make a radio call on 121.5.
Mayday, mayday, mayday. 52241, says the 172, engine failure. Forced landing 5 miles southeast of Kiowa, one on board.
If possible, try to set up your emergency approach just like a normal approach with downwind, base, and final legs. Your downwind position should be about 180 degrees from where you want to touch down. Once you are assured of making your selected landing site, begin to secure the airplane to reduce the risk of fire. Cut the fuel to the engine by bringing the mixture to idle cutoff. Turn the fuel selector to the off position. Then turn the ignition switch off. Lower the flaps as required. And then turn the master switch off. Unlatch the doors prior to touchdown to make it easier to exit the airplane if it is damaged during the landing. In a real emergency, be prepared to touch down on a surface that is much rougher than what you're used to. Hold back pressure on the yoke to lower the nose wheel slowly. This will reduce the chance of the airplane flipping over if the surface is soft. Apply the brakes as needed. On a short field, you may need to apply the brakes heavily. Practice emergency approaches will typically end by going around once you are assured of making the selected landing spot. Try and make your practice approaches as realistic as possible. Look for a spot that you could really land on and concentrate on making a good approach. Being prepared is the best line of defense in an emergency situation. An emergency approach and landing is a skill you may never have to use, but it sure pays to know how to do it well.
As you continue your training, you will be introduced to more advanced flight training, including maneuvering during slow flight. Slow flight can be thought of as any airspeed below normal cruise. However, during your training, slow flight will typically be conducted at an airspeed where any significant reduction in speed or power or an increase in load factor results in a stall indication. You should practice maneuvering during slow flight to develop a feel for the controls at various speeds and power settings, and to learn the relationship of power and pitch to altitude and airspeed. Before you begin the maneuver, check for other air traffic by clearing the area.
There's traffic at 10 o'clock. Let's turn right about 90 degrees.
To transition from cruise flight, first apply carburetor heat and then reduce the power to several hundred RPM below that used to maintain cruise altitude. Remember, as you decrease the airspeed, you must also increase the angle of attack to maintain altitude. During this time, use trim to remove control pressures. When the airspeed approaches the desired value, increase power to hold the assigned airspeed and altitude. As power is added, smooth application of the right rudder is required to overcome the airplane's left-turning tendencies. Then, when attitude, airspeed, and altitude stabilize, trim the airplane to relieve control wheel pressures. The attitude indicator confirms the airplane's high pitch condition, while the altimeter and the vertical speed indicator verify that you're level. At these slow speeds, control response will feel sluggish, although greater control deflections may be needed to achieve a change in flight attitude. You should apply gentle control pressures. Using abrupt movements could result in a stall. While operating in slow flight, any attempt to change altitude solely through the use of control pressures will not achieve the desired results. For example, if you attempt to climb by just increasing the pitch attitude, the airspeed will decrease, and the airplane will stall. The correct procedure is to apply power, then adjust the pitch attitude as necessary to maintain the desired airspeed. On the other hand, if you decrease the pitch to descend without reducing power, the airspeed will increase above that desired. The proper way to descend is to reduce power and adjust the pitch attitude. Climbing and descending in slow flight demonstrates that power controls your altitude when you maintain the same airspeed. To turn the airplane during slow flight, the same procedures used at higher speeds are still applicable. However, in slow flight, you must add power to maintain altitude. Whenever you make a turn during slow flight, use shallow bank angles and smooth, coordinated control wheel movements to prevent stalling the airplane during the turn. Your instructor will also have you practice slow flight with various flap settings, so you can see the different attitude and power requirements for each phase of flight. To return to cruise flight, apply full power and slowly decrease the pitch attitude as the airplane accelerates. As the airspeed increases, retract the flaps if extended. After reaching your cruise airspeed, adjust power and trim for cruising flight. Maneuvering during slow flight provides you with a better feel for the airplane in various flight conditions. This will help prepare you for several aspects of flight training, including stalls and landings.
When maneuvering during slow flight, you are flying very near the stall speed of the airplane. But you don't necessarily have to be flying at slow airspeeds for a stall to occur. A stall can happen at any airspeed and in any flight attitude. This program will explain how to recognize an approaching stall with the power off and the procedures for recovering from a power off stall. Simply stated, a stall occurs when the critical angle of attack is exceeded, causing the smooth airflow over the wing surface to break away. This results in a loss of lift. You practice stalls for two reasons. First, they acquaint you with the stall warnings and handling characteristics of your airplane as it approaches a stall. And second, they develop your skills so you can recover from an inadvertent stall quickly and efficiently with a minimal loss of altitude. Stalls are practiced at an altitude that will allow you to complete the stall recovery no lower than 1,500 feet above the ground. Before starting the maneuver, clear the area. Then, reduce power and slow the airplane to the normal glide airspeed. As the airspeed enters the white arc, extend the flaps to the setting used during a normal approach, and establish the landing attitude. Once stabilized, smoothly raise the nose to an attitude which will induce a stall. To help determine when your airplane is approaching a stall, there are several cues you should be familiar with. One of these is the decreasing sound as the airspeed decreases. Another cue is the stall warning, which begins around 5 to 10 knots above the stall. This warning may be either a light on the instrument panel, a warning horn, buffeting of the airplane, mushy controls, or a combination of these. As the airplane nears a stall, control effectiveness decreases, and you may feel the airplane begin to shake slightly or buffet. During this time, you still have full control of the airplane, meaning you can still maintain attitude, heading, and altitude. This stage of flight is sometimes called the incipient stage of a stall, or an imminent stall. If recovery is not made at this point, a stall occurs. In a stall, the wings no longer sustain the lift necessary to maintain flight. Once the critical angle of attack is exceeded, the nose will pitch downward. Initiate the recovery by smoothly reducing the angle of attack as you apply full power. As you add power, you'll need to increase right rudder pressure to keep the ball centered in the turn coordinator. Then, use the flap retraction procedures specified by the manufacturer. As the airspeed begins to increase following the recovery, gently establish a climb attitude. If this isn't done properly, and you increase the pitch attitude too quickly, a secondary stall could occur. Conversely, waiting too long to establish a climb attitude could result in excessive speed and loss of altitude. The correct procedure is to raise the nose smoothly to the proper pitch attitude and climb at the airspeed recommended by the manufacturer. Once you've achieved proficiency in straight-ahead stalls, your instructor will have you do power-off stalls while in a turn. You will use the same procedures as in the previous maneuvers, except you will enter a coordinated turn of approximately 20 degrees before increasing back pressure on the control wheel. Recovery is much like the straight-ahead stall, except that you must level the wings. However, don't level the wings until you've reduced the angle of attack and have added full power. Then, roll the wings level by using coordinated ailerons and rudder pressure. If you're using flaps, they should be retracted, as specified by the manufacturer. Practicing stalls is not meant to increase your ability to stall an airplane, but to help you recognize the onset of a stall and how to prevent it. Or, if one does occur, what procedures to use to minimize the loss of altitude. In addition, by practicing a power-off stall, you'll get a better idea of what can happen during an approach to landing if your attention is diverted from flying the airplane.
A power-on stall can occur if you attempt to lift off and climb out at an airspeed below that normally used for takeoff, or if you use too high of a pitch attitude when trying to clear an obstacle. As with power-off stalls, learning to recognize the sensations and visual cues that precede a power-on stall will help you avoid accidentally entering into one. Remember, you should practice stalls at an altitude that allows recovery at least 1,500 feet above the ground. After the area is cleared, reduce power. And as the airplane is slowing to liftoff speed, lower the flaps if appropriate. As the airspeed decreases, increase back pressure to maintain your altitude. When the airspeed has decreased to near liftoff speed, simultaneously add back pressure as you advance the power to the takeoff or climb setting recommended by the manufacturer. The power-on stall is initially performed with the wings level, but to simulate a turn after takeoff, your instructor will also have you enter a 20-degree bank to the left or right. Remember, as you add power and continue to increase back pressure, you must compensate for the airplane's left-turning tendencies by keeping the airplane in coordinated flight. The pitch attitude for a power-on stall will be much higher than for a power-off stall. But, like the power-off stall, you will feel the characteristic buffet just before it occurs. Since you still have control of the airplane at this point, recovery from the near stall condition can be made by decreasing the pitch attitude as you apply any remaining power. Then the wings should be rolled level. When there is no danger of a secondary stall, return to straight and level flight or a climb by retracting the flaps if they were used. However, if you don't recover at that point, the airplane will stall and the pitch attitude will decrease abruptly because of the excessive nose-high attitude. If the airplane is not in coordinated flight when the stall occurs, one wing may stall first, causing a sudden roll as the nose pitches down. If the airplane is slipping to the inside of the turn, the upper wing will stall first. In this case, the airplane might roll in the opposite direction, lessening the bank angle. Conversely, if the airplane is skidding to the outside of the turn, the lower wing will tend to stall first. This results in a steeper bank. If the airplane is properly coordinated, it will pitch down with approximately the same amount of bank. Therefore, you should work to keep the aircraft in coordinated flight as you practice any power-on stalls. As your stall training progresses, you'll be introduced to several aspects of stall spin awareness. Although you are not required to demonstrate spin recovery on your private pilot practical test, you are required to have a thorough understanding of spins and spin recovery techniques. Your training in this area consists of both ground and flight instruction. The ground training portion includes instruction in the areas of stall awareness, spin entry, spins, and spin recovery techniques. Then, as your flight training progresses, further emphasis is placed on stall recognition and recovery, and realistic distractions are introduced during flight at critically slow airspeeds. It's important to remember that actual spin training is not required, and under no circumstances should you practice spins or spin recovery techniques without a certified flight instructor on board.
Accelerated maneuver stalls are a variation of power-on and power-off turning stalls. Although not included in the private pilot PTS, your instructor may demonstrate how an airplane can stall at higher airspeeds due to the additional load factors created by a steep turn. For example, in a 45-degree level turn, the airplane's effective weight is 1.4 times greater than in level flight. This means that if the normal stall speed for a particular airplane in straight and level flight with flaps up is 50 knots, it will stall at 59 knots in a 45-degree level turn. Before beginning an accelerated stall, clear the area. Then verify that the airspeed of the airplane is below the published maneuvering speed. This will avoid placing high structural loads on the airplane during the maneuver. Next, roll the airplane into a level bank of approximately 45 degrees and firmly increase back pressure on the control wheel to initiate a stall. Normally, you will recover at the first indication of a stall by releasing back pressure while simultaneously adding full power. Then, use the flight controls to keep the airplane coordinated as you level the wings. A crossed control stall is most likely to occur during a poorly planned and executed turn from base to final approach, and is often the result of overshooting the extended runway centerline during the turn to final. Even though flight proficiency in a crossed control stall is not required, it will be demonstrated to you by your flight instructor. The important thing to understand is not how to perform the crossed control stall, but to be able to recognize its onset and the procedures necessary for a safe recovery. A crossed control stall will occur when you apply aileron pressure in one direction, rudder pressure in the opposite direction, and use excessive elevator back pressure. Stall should be practiced at an altitude that will allow you to safely complete the stall recovery no lower than 1,500 feet above ground level. For this demonstration, we'll check the area for other traffic, reduce the power, then maintain altitude until the airspeed approaches the normal glide speed. Flaps should not be lowered during this demonstration because of the possibility of exceeding the airplane's limitations. Once the glide attitude and airspeed have been stabilized, roll into a medium bank turn to simulate a final approach turn with an overshoot to the center line of the runway. Continue the turn while applying full rudder input in the direction of the turn. Maintain the bank by applying opposite aileron pressure to stop the overbanking tendencies, while slowly increasing back pressure on the elevator to keep the nose from lowering. When the airplane stalls, release the pressure on the flight controls, and then increase the power as necessary to return to straight and level flight. In a crossed control stall, the airplane may stall with little or no warning. The nose may pitch down, and the inside wing suddenly drop. The airplane may continue to roll into an inverted attitude. This is usually the beginning of a spin and can be very dangerous at lower altitudes. Early recognition of the characteristics of a crossed control stall is very important because recovery may be impossible due to the altitude needed for a safe recovery. The demonstration of an elevator trim stall will show you what can happen when full power is applied during a go-around from a normal landing approach, a simulated forced landing, or immediately after takeoff with an improperly set takeoff trim setting.
Whenever we're practicing stalls, John, one thing you've got to remember, according to the PTS, is that we must recover from a stall no lower than 1,500 feet AGL.
Even though flight proficiency in an elevator trim stall is not required, it will be demonstrated to you by your flight instructor. The important thing to understand is not how to perform the elevator trim stall, but to be able to recognize its onset and the procedures necessary for a safe recovery. You will also learn the importance of making smooth power changes, how to overcome strong trim forces, and how to maintain positive control of the airplane in a go-around environment. After clearing the area for other traffic, slowly reduce the power. Lower 1/2 to full flaps. Then set the power to idle. Maintain altitude until the airplane slows to the approach glide speed. Once established in a glide, simulating the final approach path to the runway,
Smoothly advance the throttle to the maximum allowable power as you would in a go-around. To recover from the approaching stall, apply positive forward control pressure to lower the nose, maintaining directional control with aileron and rudder pressure. Maintain forward pressure until a normal climb airspeed and attitude can be established. Then retrim the aircraft to remove excessive control pressures. It is imperative that a stall does not occur when full power is applied during a go-around from a normal landing approach, a simulated forced landing, or immediately after takeoff with an improperly set takeoff trim setting, because the amount of pitch change and altitude needed for a recovery may be inadequate. From this demonstration, it is apparent that stall recognition is important, and prompt recovery procedures should be implemented immediately to prevent a fully developed stall condition.
After gaining proficiency in stalls, you will be introduced to more advanced maneuvers, such as constant altitude steep turns. This maneuver consists of a constant altitude 360-degree turn with a bank angle of 40 to 50 degrees. The practical test standard, PTS, requires that you be able to turn in both directions. Steep turns help you develop coordination of pitch and bank while maintaining altitude at a constant power setting. They also develop smoothness, orientation, and division of attention. Before you enter the maneuver, make sure there is no conflicting traffic in the area. To maintain orientation, select a reference point parallel to your flight path. Section lines, roads, or a prominent landmark on the horizon are all good reference points that help you determine the starting and ending points of the maneuver. Begin the maneuver with the airplane stabilized in straight and level flight at an altitude that will allow you to complete the maneuver no lower than 1,500 feet above ground level. Your airspeed should be at the manufacturer's recommended speed, or, if none is given, at or below maneuvering speed. Roll into a 45-degree bank turn with coordinated aileron and rudder pressure. This bank should be smoothly established at a moderate rate without rushing. As the bank steepens, you will need to increase back pressure and add power to maintain level flight. If you do not maintain the proper pitch attitude, the aircraft may enter a steep descending spiral. The natural reaction in this case is to increase control wheel back pressure, which only tightens the descending spiral and increases the possibility of an accelerated stall. If you're losing altitude and the pitch attitude is low, decrease the angle of bank slightly, then bring the pitch attitude back up to level flight and return to the desired bank angle. When you roll out of a steep turn to a designated heading or to your reference point, use the same procedures as for shallower banks, but initiate the rollout approximately 20 degrees before reaching the desired heading. As the bank decreases, reduce back pressure to maintain altitude and adjust the power to return to cruise. If you use trim during the turn, the last step is to relieve control pressures by retrimming the airplane. As you gain proficiency in steep turns, you may learn to continue from one turn to another without hesitation between the two. The back pressure held in the first turn is reduced during the rollout, then reapplied as the angle of bank increases in the turn to the opposite direction. During this maneuver, you will most likely experience an overbanking tendency. This is due to the wing on the outside of the turn traveling a greater distance than the inside wing. Since it is traveling farther, it has a faster airflow. As more air passes over an airfoil, more lift is produced. This increase in lift on the outside wing causes the airplane to roll beyond the desired bank angle. To counter this tendency, you must apply slight aileron pressure opposite the direction of turn. In addition, because the tail of the aircraft is located aft of the center of gravity of the airplane, it does not track in the same arc. To streamline the fuselage, you need to apply rudder pressure. As you practice steep turns, you will begin to gain confidence in controlling the airplane while your attention is diverted outside. Developing this important skill helps you progress easily into the more advanced ground reference maneuvers.
The ground reference maneuvers in this program are designed to help develop your ability to compensate for wind drift and control the airplane while your attention is diverted outside. Many of the skills you'll learn in these maneuvers can be applied to your routine flying and improve your feel for the airplane. The first step in executing any ground reference maneuver is to determine from which direction the wind is blowing. This can be done by noting the position of the wind sock at the departure airport, the runway in use, or the direction the wind is blowing trees and dust. Another method you can use is to fly a 360-degree constant airspeed, constant bank turn. The difference between your starting and ending points gives you the general idea of the wind direction. Let's begin with a look at rectangular courses. The procedures you use to fly a traffic pattern are very similar to those you'll use to fly a rectangular course. The exception is that you'll fly at a constant altitude between 600 and 1,000 feet AGL. As the name implies, you'll be flying a rectangle around reference lines on the ground. The objective is to maintain an equal distance from the boundary throughout the maneuver. This distance should be about 1/4 to 1/2 mile. Ideally, one leg of the pattern should be directly downwind. This allows you to fly one segment with the wind, another directly into the wind, and two legs with a crosswind. The preferred entry to the rectangular course is on the downwind leg in straight and level flight. At this point, the ground speed is higher than on any other leg in the pattern, and little or no crab angle is needed. When you're opposite the corner of the field, start the turn to crosswind. Since the ground speed is high, the initial bank angle is steep. But to maintain a constant distance from the field, the bank is gradually reduced as your ground speed slows during the turn. The turn to the crosswind leg is completed so that a crab angle is established into the wind. Maintain a crab angle that will allow you to fly a straight line at an equal distance from the field. The turn to upwind is begun when you're opposite the end of the field. During the turn, your ground speed slows as you head into the wind. Therefore, the angle of bank gradually decreases. This leg is flown directly into the wind, so no crab angle is required, and your ground speed is slow. During the turn to the next leg, your ground speed gradually increases. This means the angle of bank must increase to maintain a constant distance from the field. On this crosswind segment, the wind tends to drift the airplane toward the field. Therefore, the turn is completed so that a crab angle is established into the wind. Maintain this crab angle until you reach the end of the crosswind leg. As you turn downwind, your ground speed increases. This means the bank angle needs to increase gradually throughout the turn to maintain a constant distance. Your ability to compensate for the wind during a turn is an important element of flying a rectangular course properly. S-turns are a series of alternating left and right 180-degree turns across a reference line on the ground. During each turn, a constant radius is maintained by varying the angle of bank to compensate for wind drift. To begin, select a road, fence, railroad, or section line which lies perpendicular to the wind and is long enough for a series of turns. Approach the road on a downwind heading at an altitude between 600 and 1,000 feet AGL. When you're directly over the road, begin your turn. At the entry point, your ground speed is high, so the bank angle is steep. As the turn continues, your ground speed gradually slows. This requires a decrease in the bank angle to maintain a constant radius. As you approach the road, the bank angle continues to decrease until you are in straight and level flight over the road. Begin a turn in the opposite direction without delay. Since the ground speed is low, the initial bank is shallow. In the second half of the S-turn, the airplane is turning from an upwind to a downwind heading. Ground speed increases as you progress, so you'll need to increase the bank angle to maintain a constant radius. The steepest bank occurs as you near the 180-degree point. Once again, you should be in level flight when you're directly over and perpendicular to the road. If the maneuver will continue, immediately roll into the next turn. In turns around a point, you'll fly a constant radius circle around a prominent reference point on the ground. You'll need to adjust the bank angle throughout the maneuver to compensate for wind drift. The point you select should be easy to distinguish, yet small enough to present a precise reference. Like most ground reference maneuvers, the entry is flown on a downwind heading between 600 and 1,000 feet AGL. You should fly to one side of the reference point at the distance you want to maintain throughout the turn. When you're opposite the reference point, roll into the initial bank at a fairly rapid rate. Since you're flying downwind, the ground speed is high and the angle of bank is at the steepest point in the maneuver. During the first half of the turn, the bank angle is gradually reduced as your ground speed decreases. This allows you to maintain a constant distance from the reference point. As you reach the upwind side of the maneuver, the ground speed is low and the angle of bank is at its shallowest point. Your ground speed begins to increase as you continue toward the downwind side of the maneuver. This requires a gradual increase in the bank angle to maintain a constant radius. You may need to fly around the point several times to get a good feel for the wind, varying bank angles, and the proper distance from the reference point. It is also a good idea to practice turns to the right as well as turns to the left.
Most of your takeoffs and landings will be made at airports with lengthy, hard-surfaced, smooth runways. However, you might at some time have to land and take off from short runways, or rough or soft surfaces, over obstacles, or you might experience any combination of these. The efficiency of your airplane depends on your ability to employ the techniques of maximum performance takeoffs and landings. Although we will discuss short and soft field takeoffs and landings separately, you will find that many times both conditions exist at the same location. When this happens, you might need to use the techniques for both. Let's begin by looking at short field procedures. Short field takeoffs begin with a check of the performance charts to see if your airplane is capable of a safe takeoff under existing conditions. This is extremely important as density altitude increases. Besides considering the runway length and takeoff roll, during training you normally assume that there is a 50-foot obstacle to be cleared after takeoff. This requires additional performance calculations to ensure clearance. The pre-takeoff checklist is basically the same as the one you use for a normal takeoff, except that you set the flaps as recommended by the airplane manufacturer to achieve a maximum performance climb. If runway length is critical, position your airplane so that you can use all of the available runway. Then, align the airplane with the center of the runway and initiate the takeoff by holding the brakes and applying full power. While this does not necessarily shorten the ground run, it does help you be sure that the engine is running smoothly. During the takeoff roll, allow the airplane to accelerate in a level attitude with the elevator in the neutral position for minimum drag. Shortly before reaching the best angle of climb airspeed, positively rotate the airplane. Maintain this attitude until the airplane has cleared all obstacles. If no obstacles are in the departure path, or after you have cleared the obstacles, adjust the airplane's pitch to the normal climb attitude and slowly retract the flaps. You must also apply special techniques when landing on a short field. The objective is to touch down near the approach end in a full stall attitude. For training, you should assume that the approach is over a 50-foot obstacle. Your preparation for the landing begins on the downwind leg of the traffic pattern, where you slow the airplane to pattern speed and extend the flaps to the first position. Apply the remaining flaps as you continue through the base leg, and after the turn to final. Reduce the airspeed progressively to that recommended by the manufacturer for short field landings. Ideally, you should conduct the final approach at a constant glide angle, airspeed, and power setting. You may need to make minor adjustments to pitch and power to maintain a stabilized approach. If you maintain the proper approach configuration, the airplane will not float above the runway and you will touch down close to the stall speed. To produce the shortest ground roll after landing, you should make sure the throttle is closed. Apply back pressure to the control wheel. Retract the flaps and apply firm and even braking action. Typically, your initial soft field training will take place on a hard-surfaced runway. Regardless of the type of practice surface used, soft field techniques are a valuable part of your flight training. If possible, complete your pre-takeoff checklist on a firm surface in an area free from loose sand and gravel. This helps to prevent propeller and airframe damage caused by flying debris. Set the flaps for the maximum performance takeoff as recommended by the manufacturer. With the checklist completed, you're ready to taxi. If the taxi area is soft, hold back pressure on the control wheel to keep the nose wheel from sinking into the ground. You should also add a slight amount of power to help keep the airplane moving. Try to clear the approach area while taxiing in order to keep the airplane moving directly from taxi to the takeoff roll. As you increase power during the soft field takeoff, you'll have to apply right rudder pressure to overcome torque, P-factor, and spiraling slipstream. In order to prevent the nose wheel from sinking into the soft runway during the takeoff roll, you need to transfer the airplane's weight from the landing gear to the wings as quickly and smoothly as possible. This is accomplished by holding back pressure on the control wheel and accelerating the airplane in a nose-high attitude. As the weight on the nose wheel is reduced, nose wheel steering becomes less effective. However, you will still have directional control because of the slipstream flowing over the rudder. You can relax some of the control wheel back pressure as speed builds up and the elevator becomes more responsive. As you lift off the runway, lower the pitch attitude and accelerate in ground effect to the best angle of climb airspeed before initiating a climb out. When all obstacles have been cleared, accelerate to the best rate of climb airspeed. Slowly retract the flaps and continue your climb. As you enter the traffic pattern and complete the checklist, you need to concentrate on performing a stabilized approach with a smooth, soft touchdown. Using full flaps during a soft field landing will help you touch down at a low airspeed. They should be applied smoothly during the downwind, base, and final legs of the approach. Your objective for a soft field landing is to transfer the airplane's weight from the wings to the landing gear as smoothly and gently as possible. The final approach airspeed that you use at a soft field is normally the same as that used for short field landings. The descent angle will depend on whether or not any obstructions are located in your approach path. The flare and touchdown require precise pitch and power control. If runway length is not a problem, you might want to carry a small amount of power during the flare out. Then, as you near the surface, smoothly raise the nose of the airplane to an attitude which resembles the climb attitude. In this way, the airplane will settle onto the ground as gently as possible. Maintain this power and elevator back pressure during the rollout to help keep the nose wheel off the ground as the airplane decelerates. Deceleration on a soft surface is generally quite rapid. Therefore, braking, other than that required for directional control, is usually not needed. Although you need special techniques when operating to and from short and soft fields, your ability to properly execute maximum performance takeoffs and landings will increase your flying enjoyment. The skills that you acquire will not only make you a safer pilot, but will enable you to use the many airports not serviced by long, hard-surfaced runways.
During VFR flight, you control the airplane's attitude and flight path by combining a general view of the horizon and what you see outside your airplane with a cross-check of the flight instruments for specific information. During instrument flight, you rely completely on the flight instruments to provide all the necessary information. Now the Earth's horizon and your outside visual references are replaced by the attitude indicator, which gives you information regarding pitch and bank. Never intentionally fly into IFR conditions without first obtaining an instrument rating. However, developing your instrument flying skills will help you cope with an inadvertent encounter with IFR conditions. As you learn to control an airplane solely by instruments, you'll develop more confidence and increase your skills in instrument interpretation and precision control. One of the first skills you need to develop is a systematic method of looking at each flight instrument. This skill is called scanning. The instruments included in your scan are the attitude indicator, altimeter, vertical speed indicator or VSI, heading indicator, turn coordinator, and the airspeed indicator. During your training, you will learn not to fixate or stare at one particular instrument, nor place too much emphasis on one indication. You will also discover that you cannot omit any instrument from the total scan. For example, if you're trying to maintain directional control by staring at the heading indicator and omit the other instruments, you might place yourself in a critical flight attitude. You can see that it's important to scan all of the instruments. Let's look at how to maintain straight and level flight by instrument reference. The objective is to fly a predetermined heading at a specified altitude. To help maintain the desired altitude, use the attitude indicator, altimeter, vertical speed indicator, and airspeed indicator. A constant power setting helps to simplify maintaining your altitude. The attitude indicator gives a direct indication of your general pitch attitude. Any changes in pitch, whether up or down, will be detected by the attitude indicator. The altimeter tells you whether you're at the desired altitude or moving away from it. For example, if your altitude begins to increase due to an inadvertent pitch change or a vertical air current, the altimeter indicates the change. But the altimeter is not the only instrument that tells you the altitude is changing. The vertical speed indicator also helps detect movement from the planned altitude. The VSI instantly indicates the trend of any altitude displacement. The actual rate of climb or descent, however, may take a little longer to register. Another instrument that indicates a change in altitude is the airspeed indicator. Once you've established a constant power setting, airspeed fluctuations signify pitch changes that will result in altitude variations. For example, if pitch increases, the airspeed begins to decrease. If airspeed increases, pitch has decreased and you will lose altitude. When you notice a change in altitude, you'll need to correct the pitch attitude to return to the original altitude. You should make corrections by referring to the attitude indicator and monitoring the altimeter to complete the adjustment back to level flight. As a general rule, if the altitude deviation is less than 100 feet, you should correct the pitch attitude without changing power. When the deviation is greater than 100 feet, you should combine a pitch change with an appropriate power adjustment. Let's look now at the other half of straight and level flight, maintaining a constant heading. The instruments used for bank control are the attitude indicator, heading indicator, and turn coordinator. The attitude indicator instantly shows any change in bank and gives a general picture of bank attitude. If you bank to the left or to the right, you get a direct indication of the movement on the attitude indicator. During coordinated flight, a turn is also shown on the heading indicator. Generally, if the heading remains constant, the wings are level. A shallow bank is shown by a slow heading change, while a rapid change signifies a steeper bank. Another instrument which provides an indirect indication of a bank is the turn coordinator. Your heading will remain constant when the wings of the miniature airplane are level and the ball is centered. You will be in a bank and subsequent turn when the wings of the miniature airplane roll to either side. With an understanding of how straight and level flight is performed, let's look at how climbs are made by instrument reference. To enter a climb from cruise airspeed, you need to raise the nose of the airplane. Monitor the attitude indicator as you increase the pitch attitude above the horizon reference line. You must also increase power to sustain the climb. Do this either simultaneously with the pitch change or after the pitch has been established and the airspeed approaches the desired climb speed. When the airspeed stabilizes, trim the airplane. During a stabilized climb, any change in airspeed signifies that the pitch attitude has changed. To correct the pitch, use the attitude indicator. Your actual rate of climb depends on the density altitude, power setting, and aircraft weight. But the VSI can provide an indirect indication of pitch changes when it increases or decreases. In a climb, you maintain directional control the same as in straight and level flight, with one exception. The ball in the turn coordinator is scanned to ensure that you are applying enough right rudder pressure. The level off from an instrument climb is performed the same as with outside visual references. As you approach your desired altitude, begin the level off by leading the altitude by 10% of the vertical speed. For example, if you are climbing at 500 feet per minute, lead the level off altitude by 50 feet. To level off, apply smooth controlled pressure until the miniature airplane on the attitude indicator is aligned with the horizon reference line. As you establish a level flight attitude, the vertical speed indicator will move slowly toward zero. The altimeter needle will slow its upward movement, and the airspeed indicator will move toward cruise airspeed. To complete the transition from climb to cruise, relax the right rudder pressure you held during the climb to maintain the planned heading, reduce power to cruise, and trim the airplane. With the airplane established back at straight and level, let's go ahead and look at how to descend by instrument reference. To enter a constant airspeed descent, establish the desired airspeed by reducing power to the predetermined setting and maintain altitude. As you reach the desired airspeed, lower the pitch to maintain the airspeed and trim for the descent. Correct any deviation in airspeed by adjusting the pitch attitude. Use the bank control instruments to maintain directional control during the descent. As you approach your planned altitude, begin the level off by leading the altitude by about 10% of the vertical speed. Raise the pitch attitude to level flight. Then increase the power while maintaining directional control. When stabilized in cruise, retrim the airplane. The next maneuver we'll look at is performing a turn. All turns by instrument reference are made at a standard rate of 3 degrees per second. When the miniature airplane in the turn coordinator is aligned with the reference mark, you are in a standard rate turn. To enter a turn, establish a bank by referring to the attitude indicator. As you become familiar with your airplane, you'll learn the angle of bank that produces the standard rate turn at a given true airspeed. As the turn is established, you'll need to raise the nose slightly to offset the loss of vertical lift during the bank. Then, check the turn coordinator to ensure you are in a coordinated, standard rate turn. If the turn is not standard, make a slight bank adjustment on the attitude indicator and confirm the change on the turn coordinator. The altimeter and the vertical speed indicator must be included in your scan to assure that the altitude is being maintained. During the turn, monitor the heading indicator to determine the progress toward the desired heading. To allow for the rollout, lead the heading by the number of degrees equal to 1/2 of the bank angle. For example, if you are in a 15-degree bank, start the rollout about 8 degrees before the desired heading. As you return to wings level, release the back pressure held during the turn and continue your instrument scan. Part of your attitude instrument training will include recognition of, and recovery from unusual or critical flight attitudes. Your instructor will have you close your eyes and let go of the controls. The airplane will be maneuvered to simulate an unusual attitude that could result from turbulence, preoccupation with cabin duties, disorientation, or erroneous instrument interpretation. When you're instructed to take the controls, you need to evaluate the situation immediately and make a proper recovery. For example, the approach to a climbing stall is signified by a high-pitch attitude and decreasing airspeed. This situation requires you to lower the nose toward level flight while immediately adding full power and leveling the wings. Conversely, if the pitch attitude is low and the airspeed increasing, you'll need to reduce power to prevent excessive airspeed, adjust the wings to level, and then raise the pitch to a straight and level flight attitude. Your initial training in attitude instrument flying does not qualify you to fly in IFR conditions without an instrument rating. However, it does provide you with basic emergency skills if you inadvertently lose outside visual references. It also helps you interpret the instruments more effectively during VFR conditions.
Night flying can offer some of the most exciting and enjoyable flying that you will ever experience. At night, there is usually less traffic. The air is generally smoother, and the communication frequencies are less congested. However, because your vision is less sharp at night, you need to pay close attention to numerous items when planning and making a night flight. Safe night flying begins with careful and thorough flight planning. Because of the visual limitations of night flying, chart references and the altimeter may be your only reliable means of determining altitudes sufficient for terrain and obstacle clearance. You should also have available the adjacent chart if your route of flight will take you near the edge of the sectional. By referring to the adjacent chart, you'll be able to identify distant cities or landmarks not found on the primary chart. Your preparation for a night flight should also include a complete weather briefing, including a study of the available weather reports and forecasts. When reviewing this material, it is important that you pay close attention to the temperature dew point spread. A small spread is a good indication of the possibility of the formation of ground fog. Because aircraft drift is very difficult to detect during takeoffs and landings at night, it's a good idea to also pay close attention to the wind direction and speed. Another important consideration is that under no circumstances should a night VFR flight be made under poor or marginal weather conditions. As you continue with your planning, it's recommended that you check the availability of airport lighting along your route of flight. This information can be found on aeronautical charts and in the airport facility directory. It's also important that you check the status of these lights by reviewing the pertinent notices to airmen. Once your planning is finished, you're ready to pre-flight the airplane. Remember that before any flight at night, you should allow at least 30 minutes for your eyes to adapt to the darkness. To ensure that you completely check the airplane prior to departure, use a reliable flashlight during your pre-flight inspection. You should also have a second, smaller flashlight in the cabin for reading or for use in the event of an in-flight electrical malfunction. As you conduct your pre-flight inspection, avoid shining the flashlight directly into your eyes. This could destroy your night vision, requiring you to readapt your eyes to the dark. Part of your night pre-flight inspection should include a check of all aircraft lighting. Besides assuring that the anti-collision lights are working, you must check your position lights, which are required by regulation for any operation between official sunset and sunrise. These lights help other pilots identify your direction of travel. When doing this, it's a good idea to tap the lens of the light to check for any loose connections. If the light blinks when tapped, the light should be fixed prior to departure. Although landing lights are not required unless the aircraft is operated for hire, most airplanes are equipped with one, and it should also be inspected. You should also check cabin lighting during your pre-flight to make sure the instrument panel is clearly visible. Once you have completed your visual inspection, it's wise to check the ramp area for hazards. Things such as tie-down ropes, chocks, and step ladders are more difficult to see at night, and a quick check of the surrounding ramp area could prevent a mishap during taxi. Before starting the aircraft, take some time to thoroughly familiarize yourself with the location of all instruments, controls, and switches. Fumbling for them in the dark can be confusing and dangerous. While cockpit organization is important at all times, it's especially important at night. Knowing where everything is located will make it easier to find your computer, sectional, or even a pencil. One way to keep from losing essential items in the dark is to use a clipboard or map board to fasten charts, navigation logs, and other essentials in a known location. As an additional aid, be sure your sectional is open to the proper panel and your route of flight is clearly visible. During an engine start at night, use extra caution. In addition to the normal call-out of clear, turning on the position lights or momentarily flashing other aircraft lights will alert others in the area. Before taxiing, especially at an unfamiliar airport, you might want to request taxi instructions. Then, when ready to taxi, turn on the taxi or landing light. Because taxi lights do not cast very wide beams and illumination to either side of the aircraft is limited, taxi speeds should be slower at night. When approaching another aircraft, be courteous and turn the landing light off, if safety permits. This will avoid temporarily blinding the oncoming pilot. As you're taxiing, if there is ever any doubt about where you are or how to get somewhere, don't hesitate to ask. It's also important to remember that when you receive a runway holding or hold short instruction, you must read it back to the controller. Answering with your call sign or Roger is not acceptable. Before taking off, it's important that you conduct a thorough run-up. Since it's not as easy to detect an unintentional forward movement at night as it is during the day, it's a good idea to use the parking brake. By carefully completing all of the items on the checklist, you can detect potential problems which might arise. Before taxiing onto an active runway for takeoff, you should carefully check the final approach course for aircraft. At non-tower airports, it is recommended that you do a slow 360-degree turn in the same direction as the flow of air traffic while closely searching for other aircraft in the vicinity. After ensuring that the final approach and runway are clear of other traffic, you are ready to taxi onto the runway for takeoff. It's important to note that during night operations, ATC will not issue a clearance to taxi into position and hold for intersection departures. During a night takeoff, the runway center line and runway lights provide visual references for directional control. As you begin the takeoff roll, maintain directional control by selecting a reference point down the runway, such as the point where the runway lights appear to converge. Having fewer reference points at night can make it more difficult to establish the proper climb attitude, especially over sparsely populated areas. Therefore, you should use your flight instruments to help establish the proper attitude. As you gain altitude, more distant highways, cities, and lighted areas may become visible. On a clear, moonlit night, it may be possible to determine the outline of terrain and other surface features. Flying at higher altitudes at night will increase your visibility for pilotage, radio navigational reception, and gliding distance. However, you need to consider the existing weather and oxygen requirements at these altitudes. Scanning at night is another important consideration. Although an aircraft's position lights enhance the see and be seen concept, you must not become complacent when scanning for traffic. Unless a conscious effort is made to separate an aircraft's lights from stars or the lights of a city, conflicting traffic can go unnoticed. One way you can help other pilots to see your aircraft is by turning on your landing light. In fact, the FAA is encouraging all pilots to turn on their landing lights when operating within 10 miles of any airport, regardless of the time of day. Another thing that can be very difficult to detect at night is changing weather conditions and cloud formations. Typically, the first indication of flying into marginal weather conditions is a disappearance of stars or lights on the ground. A halo or luminous glow around the position lights or a reflection of the landing and anti-collision lights may indicate you have penetrated an area of haze or clouds. If you inadvertently enter these conditions, you should immediately use instrument references to establish control of the airplane in straight and level flight. Then note your present heading and make a 180-degree turn back to visual conditions. To help avoid accidentally flying into instrument weather, you should continually update your weather briefing by contacting En route Flight Advisory Service or any flight service station along your route. Your concern for changing weather conditions should be combined with careful planning for emergencies. If you need to make a forced landing, finding a suitable field presents special problems. The nature of the surface and terrain is difficult to see, even on a bright moonlit night. Although highways may provide places to land, you need to be aware of the possibility of power lines that are often located along and across them. As a safety precaution, many pilots alter their route at night to keep within a reasonable distance of lighted airports for most of the flight. When approaching an airport at night, it may be difficult to identify the runway layout until you are almost on top of the airport. For this reason, you should fly toward the airport beacon light until the lights outlining the runway are distinguishable. To fly a traffic pattern of the proper size and direction, the runway threshold and runway edge lights must be positively identified. Once seen, the approach threshold lights should be kept in sight throughout the airport traffic pattern and approach. To conclude your flight, the same landing procedures and techniques used during the day are also performed at night. However, runway lights, airport lights, city lights, and the airplane's landing light may create illusions not encountered during daylight. Thus, speed, altitude, and distances may be more difficult to judge. If glide slope information, such as a VASI or PAPI, is available, it will help you maintain the proper descent attitude. By carefully monitoring your flight instruments and power setting, you can help to ensure a smooth approach and landing. You should practice night landings both with and without the landing light to enable you to make a safe landing in case the light fails. Although special consideration is needed at night, proper preparation and flying techniques will help to make flying at night a very enjoyable experience. Your ability to go from daylight to the night environment will not only add to your airplane's usefulness, but it will also increase the pleasure you receive from flying.